Hi, today I'm glad to welcome François Sindt, who will present his last publication. François is currently a PhD student at the Laboratoire d'Innovation Thérapeutique from the University of Strasbourg, and is going to talk about a new approach to identify heat from ultra-large chemical spaces.
So thank you for this introduction and the opportunity to present this work, which is related to an organic chemistry-driven virtual screening method that allows to explore very large chemical space. So the commercial available chemical space is growing up very fast the last year. 10 to 15 years ago, we were only at the scale of a million of purchasable molecules with a growth rate of 500,000 per year. And right now, we can easily purchase 50 billion of molecules. For example, the NA mineral space scales up right now to 48 billion, and you can purchase them in 3 or 4 weeks. And in structure-based virtual screening, it starts to be a problem in terms of calculation time. And so right now, there is a significant interest, a real interest to find a new method that can deal with hundreds of millions, even billions. If anything go to trillion, it's nice. And because when you screen virtually a large space, you have more chance to find hits, and your hits will be more potent. So the method that I would like to show you today is called SpaceDoc. And instead of going through one by one to each compound like a classical virtual screening method does, here we screen virtually chemical reagents, so building block of a provider. For example, in this picture, you have building blocks from enamine everywhere into the binding site, generated by molecular docking. And the algorithm go through pairs of building block, and it checks if the building blocks are compatible for a common organic reaction, and if their relative position is suitable for the connection of a single bond or a ring formation. And in that case, we have a good match for Suzuki coupling. So we connect two building block docking pose directly inside of the binding site. And we minimize the structure to refine, to relax the newly created bond. And the real advantage of these techniques is because it's combinatorial, you can explore hundreds of millions, even billion of molecules only by screening virtually few 10,000 of building blocks. So to validate our methodology, we decide to target the dopamine D3 receptor to find new antagonists. So we use molecular docking to generate conformation of 20,000 carboxylic acid and 33,000 amine inside of the orthosteric binding site to explore 670 million of carboxamide. This has been done in 2 weeks over a reasonable amount of CPUs. And to compare with a classical docking protocol, to explore the same chemical space, it takes more than 6 months. So we managed to connect 24 million times a pair of building blocks in silico synthesis. After a series of filters, we managed to isolate 315 virtual hits. We purchased 15 of them, directly accessible into the real space of enamine. We test this molecule to their ability to bind the dopamine D3 receptor. And we got a 66% hit rate at 10 micromolar, and 6 of 15 of these compounds were very low micromolar, even nanomolar compounds. So the next, the perspective is dealing with 3-component reaction. For example, by coding the petasis reaction, and with almost 50,000 building blocks from enamine, we can right now explore chemical space at almost trillion scale. So thank you for your attention. And if you would like more details on the methodology, you can check our paper in ACS Central Science.